Before moving on into our last concept of the course, need to talk a little bit about something called a discontinuity. Now, we've talked before about continuous functions and what that means. If you recall, continuous, or at least our definition of continuous, was that if you take your pencil and try to trace the graph, you can trace the entire graph without lifting up your pencil. So there are no asymptotes, there are no gaps or other holes or things to jump over. You can make one smooth curve, like, for example, the graph of sine of x, or any linear function or quadratic, any polynomial function for that matter. Rationals, not continuous. So we need to talk a little bit about discontinuity to sort of finish up this material. And we've seen examples of discontinuities. In fact, rather than define the term, because the definition is a little on the funky side and can get somewhat abstract, I'll use examples to help us get a sense of what it is. Any vertical asymptote is a discontinuity. That's a place where we have to pick our pencil up, jump over the asymptote, and continue. For example, I'll just sketch a little graph here. Something maybe like this. Something like this. And like so. Here is a discontinuity, something that causes the graph to not be continuous. And notice I only use the term vertical. Horizontal asymptotes can be crossed. So can a slant. They can be crossed in the short term, and in the long run they're approached. So because they can be crossed, it's not necessarily a discontinuity. Horizontal asymptotes have nothing to do with where the function is undefined. We have another type of discontinuity that we've seen before. When we looked at piecewise functions, we saw that some can have holes. For example, I'll sketch another graph here. Here's a graph that would be defined, or here's a function that would be defined piecewise. There are two pieces. And here we have a discontinuity. We have a gap. Sometimes it's referred to as a hole. The more appropriate term, I think, would be gap. Now, there's a place where if I'm sketching this, if I'm following the path, from here to here, I got to pick up my pencil and start over. I have to jump over that gap. There's a hole there. There's a gap there. Now, to confuse you a little bit, there's a different type of hole. There's a hole in something that's not considered to be piecewise. So something that looks like this. It looks like it's a linear function, but there's a hole here. There's a hole there. It's as if we just chose a point to take out and say, oh, that point's an open circle, everything else is good. It's a different hole than this. That's why I like the term gap instead. I'm just going to make the executive decision. We'll call those gaps, not holes, because this is more appropriate for a hole. It's just like there's one little piece missing. And we're going to look at a few of these examples here so we get a better sense of where they are and why they exist. And I'm going to clarify the why by saying, in order to get a full understanding of the why, that's better reserved for calculus in the fall, because that you'll have the tools by then to better deal with why holes exist. I'll give you a kind of sort of explanation that hopefully makes sense coming up, but the full picture will be unveiled, I would guess, late September, early October in the fall, for those of you that are taking the calculus journey. So let's look at a function. Here's a function. And let's use some of our analysis tools that we've had for the last couple of weeks to analyze this function. First of all, we notice that the degree of the numerator is greater than the degree of the denominator, which tells us if we were to graph this, we would have a slant asymptote. And I would tell you that normally that's correct. But in this case, it's actually false. There is no slant asymptote on this function. And if you're confused, take a closer look at the numerator. There's something we can do to the numerator. Before you cancel anything, do not lose the original function. Do not lose the original function. Don't erase this. Keep it. Yes, you can go ahead and cancel those factors. We have reduced the function to x minus 2, but do not lose this. Do not lose this. So, we have turned a rational function into what looks like a linear function. That's kind of sort of accurate, but it's not the whole picture. Let's look at the domain of f of x. Domain. There's our domain. Now, if you are yelling at your computer screen right now or your phone, just screaming that, wait a minute, we got rid of the x minus 3. No, we didn't. We did no such thing. The domain of this function, the domain of this function, not the domain of this, the domain of the original function is negative infinity to 3 union 3 infinity. That's the domain. If I plug 3 into the original function, it fails. And we have to deal with the original function. Yes, this is nice and convenient 99.99999% of the time. But it's not the original function. It's a simplified version for convenience. It is not f of x. This is f of x. This is f of x. Now I grant you that if I plug 0 into f of x, and I plug 0 into here, I will get the same answer. If I plug in 1 to both, I get the same answer. If I plug in negative 32,115 in both of these places, I get the same answer. But if I plug in 3 and I plug in 3, that's where trouble occurs. That's a problem. 3 is not in the original function's domain. Therefore, it cannot be in this simplified domain. Again, if you are not satisfied with that reasoning, I've got a little better one coming, but to be fully satisfied, you have to wait till the fall. And if you're not taking calculus in the fall, hopefully someday you will take it, and then you will be satisfied at that point in time. Let's move on to vertical asymptote. I'm going to confuse you again and say there's none. There is none. There's not a vertical asymptote here. I'll explain why shortly. Zeros. What value or values make f of x equal to 0? Two. When x is 2, y is 0. When x is 2, y is 0. I've already said there is no slant asymptote. We know there's not a horizontal. Now we have something new. We have a hole. Where's the hole? It's x equals 3. Now, some of you are probably just pulling your hair out, or you might be punching your monitor, your screen, just in utter confusion / frustration. But let me alleviate some of that. Let's go, let me just insert a new page here. And yeah. Let's take a look at a function that is a little more familiar. So we're just going to take a little time out and look at a different function for a second or two. 1 over x minus 4. You know there's a vertical asymptote there. It's at x equals 4. You know there's, oh shoot, I don't want to do that. I'm going to change our function just a little bit. There we go. We know there's a 0 at x equals negative 1. We know that. X equals 4, x equals negative 1. These are not the same thing. Now let me go back here for a moment. I'm going to choose, I want a color that's awful. We'll go with this color. This color is awful. I'm going to choose an awful color for a moment. I want to look at this factored version of our function. Find the zeros. We found x equals 2, and we found x equals 3. Oh, that color is hideous. Perfect. Let's find vertical asymptotes. X equals 3. And notice the problem. We have a vertical asymptote a number that x can't equal, and we have the same number being a 0. In other words, if I plug 3 in for x, I get y equals 0. I get f of x equals 0. Can't have a value of x. Here's a solution to the equation. But we can't have that value. Even though it's a solution to the equation, we can't have the value. See, the problem here, we're going back and forth. We have an answer, we have a root, we have a 0, a solution that is also an asymptote. We can't have that. Which is why we remove it and create a hole. We create a hole in the function because of that. Now again, this is not f of x. This purple part is not f of x. It's a reduced form to make it easy to graph and to make it easy to calculate things. However, we have to put this restriction on it. Because this graph is linear, or this reduced form is linear, linear functions don't have asymptotes, which is why the slant went away. And if you don't believe me, let's graph this. Let's graph this. I have it preloaded, all set to go. Graph. Would you look at that? I think I did something wrong here. No? That's right. Something's not right. Oh, shoot. I have a problem. I factored it incorrectly. This should be positive 2. That should be negative 2. Negative 2 is a 0, not positive 2. Yeah, that's better. Here's a graph. Let me blow it up. There it is. When x is negative 2, y is 0. Oh, look, when x is 3, y is something. So if you're saying, wait a minute, there's no hole there. What are you talking about, crazy guy? There's no hole. I contend there is. Second table. Uh-oh. X equals 3 says error. There's a hole there. Because the calculator doesn't like holes, and because the hole is such a very small point compared to all the points here, it just kind of sort of connects it anyway. There's a hole there that you just can't see. You just can't see the hole, but it's there. So here's a graph of that function. This is x equals 2. There you have it. Now, let me see if I can help you understand why the hole is there a little better. I'm going to go back to the original function, and I'm going to plug 3 in for x. 3 squared is 9, minus 3 is 6, minus 6 is 0. Plug 3 in for x in the denominator. We get 0 over 0. And that's bad. That's worse than bad. This is bad squared. We know dividing by 0 is bad. Well, 0 divided by 0 is worse. Way worse. Way, 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 way worse. I'm going to go back here to my little scratch paper screen here. Before I do that, notice the difference between this now and this. Let me go back here. Vertical asymptote, 0. Completely different values. Vertical asymptote and a 0 that are the same. That's bad. That creates the hole. That's why we put a hole there, because this value showed up in both of these spots. We don't put it in either spot. We create a new category. We say it's a hole in the graph at x equals 3. And why did I label that as 2? Second mistake today. This should be 3. It's 2 mistakes today. Must be Friday. Hole at 3. Plugging in 3 gives us 0 over 0. Now, you might say to yourself, wait a minute, if I plug 3 into this, I get 1. 1, 2, 3. Yeah, I don't think that's 1. I'm not sure what my scale is here. Let's take a look. Let's go back to the table. Oh, that looks like it's going to be at 5. Oh, dummy, that's because I didn't fix that. There we go. X plus 2. Wow. There's a hat trick of mistakes. Really must be Friday. My brain is on the weekend already. Okay. Let's no more mistakes from this point forward. If I plug 3 in for x, I should get 5, according to that simplified form. Yeah, it kind of looks like that makes sense. But again, there's that error because plugging in 3 gave us 0 over 0. Now, why is that bad? Why is that worse than bad? Why is 0 over 0 bad squared? Because it is really, really, really bad. I'll give you as simple of an answer as I can. I'm going to start with a few examples. 3 divided by 3, that's 1. 8 divided by 8, that's 1. 14 to the 372nd power over 14 to the 372nd power, that's 1. So 0 divided by itself should equal 1. Anything divided by itself equals 1, according to this rule. Well, let's take 0 divided by stuff. 0 divided by 3. 0 divided by 8. 0 divided by 1, whatever this number is. That's a big number. So, following this rule, 0 over 0 should be 0. If we're allowed to divide 0 by 0, then that means the number 1 has to equal the number 0. That means 0 and 1 are exactly the same. If 0 over 0 is allowed, then 1 gets to equal 0. And we don't want 1 to equal 0 ever. That's why this is bad. Worse than bad. It's bad squared. It's terrible. Therefore, 0 over 0 is called an indeterminate form. It's an indeterminate form. An indeterminate form is something that calculus people will learn about in the fall. I will leave it there. We can't determine it because we don't know which one of these is actually correct. If either one is correct, we can't determine that. We don't know if 0 over 0 should be 1 or follow that rule, or if we should follow the rule that 0 divided by anything is 0. We have two rules that are in conflict. They both can't be right. So if we're allowed to say 0 over 0 exists, that means both of these are allowed to exist at the same time, and both of these are allowed to be equal, which means 1 equals 0. Which means we could really screw up all the other rules of algebra and arithmetic if one is allowed to be 0. That means the number 100 would be exactly the same as the number 111, because I could pull out all the ones and exchange them with zeros, and pull out all the zeros and exchange them with ones. That means the number 1000 would be the same as 0. Things get messy. So we do not allow it to be determined. It's indeterminate. It's indeterminate. By the way, calculus people, you will like 0 over 0 next fall, because when you get 0 over 0 doing certain types of problems, things get really nice. I'll leave it there. So let's go back to our example here. We get, by plugging in 3, we get this indeterminate form. We can't have that. So we say, all right, look, even though we reduced this to a linear equation, not a function, we reduce this to a linear form, we still cannot allow 3 to be plugged in. We can't do it. So we're going to put a hole there and just say that doesn't exist. We take it out of the domain. We don't need a vertical asymptote, because when we graph every single other point, we do get what appears to be a line, but it's not a line. Okay? Okay. I'm going to show you one example that's similar to this. You might notice that there's something behind here. Here's why that hole is important, and why we can't say this is a function. In other words, we can't say that this replaces this. I'm going to put a little separation here so we don't get confused. So here I have a second function, g of x. Let's take a look at factoring this. X minus 4, no mistakes this time. And I go cancel, cancel, and I get x plus 2 again. Wow. The graph of this and the graph of this are identical, right? Because they both reduce to the same thing. Cool. I have that one all queued up and ready to go. I just have to turn this one on. And when I graph it, let's get the big screen. The graphs are identical. They're the same thing. No. They are not the same thing. That's another reason we need the hole. These are not the same things. Don't believe me? let's go to the table. Here's the first example we did. Here's f of x. Bad at 3. Now in g of x, 3 gives us a number. 4 doesn't. They're not the same thing. There's a hole at 4. Again, the calculator will not show the hole because it doesn't like problems. Part of its programming is to avoid dividing by 0 and to avoid indeterminate forms. So it skips over that and just kind of, yeah. In fact, if I go to dot mode here, let's see if, actually not sure what's going to happen. Dot mode, yeah, it did the same thing. Okay. On some models of calculator, dot mode will show a bunch of dots instead of connected points. It'll show individual points, and it sometimes puts a little bigger gap where there's supposed to be a hole. But this one's not doing it. But again, we have to tell ourselves there's a hole there. When we graph it, there's a hole there. When we write its domain, 4 can't work. The domain of g of x. Now I chose green, and you didn't. There we go. G of x, domain. Negative infinity, problem at 4. Union for infinity. Still no vertical asymptote. Still have a 0 at the same place. So that checks. That works. This works. Hole at x equals 4. The hole will now be at x equals 4. So these are not the same things. Even though they simplify to the same function, or you can't say function, they simplify to the same form, they are not the same graph. This one has a hole at x equals 4. F of x had a hole at x equals 3. But otherwise, they look identical. Otherwise, they're identical. Okay. So those are two examples of where we have a discontinuity where there's just a hole in the graph. Not an asymptote, but a hole. Okay. I have one more example. It's f of x from a little bit before, but now I flipped it. Let's see what happens. X minus 3 over, and factor this. This cancel, cancel. And I get 1 over x plus 2. What's going to happen here? 1 over x plus 2. So let's check. Domain. We have negative infinity to negative 2, union, negative 2, positive infinity. Like so. Zeros. What value of x makes the function equal to 0? Well, I got a problem. 3. 3 is 0, but 3 is also going to lead to a vertical asymptote. So, problem. There are no zeros on this one. Let me get the awful color. Even though we're going to make that go away shortly. Vertical asymptote. We have 1 left over. Negative 2. awful color says x should also equal 3. So again, here's our problem. I have a 0 and a vertical asymptote. Whole at x equals 3. The graph of this function, it's rational, 1 over x plus 2. That's rational. We know that 1 over x kind of comes down like this, and then it goes like this. Oh, we also have one more. We have a horizontal asymptote. The degree of the numerator is 0. The degree of the denominator is 1. So at y equals 0, we have a horizontal asymptote. Back to the graph, we know that 1 over x goes like this and like this. This shifts everything over 2 units to the left. So our graph kind of sort of looks like this. Here's our vertical asymptote at -2. Like this. And like this. But there's one addition I need to do here. At x equals 3, there's a hole. So now I have a rational function with a hole at x equals 3. Let's confirm that with the calculator. Clear this, clear this. This was 1 over x plus 2. I think. Yes. 1 over x plus 2. And then here's our vertical asymptote. Let's go to the table, and we should see, oh, whoops. I need to graph the original function. X minus 3 over, that's a problem. I need to graph the original function. That's why it didn't work. X minus 3 divided by, this was x squared minus x minus 6. It's a good thing this is the last video of the week. These mistakes are just piling up today. Minus 6. Okay, graph. But it looks the same. Yeah, but let's go to the table and see the difference. Now we have a hole at 3. So we have an error at -2. That's expected. That's our vertical asymptote. But now we have another hole at x equals 3. Because when x equals 3, even though we can't see it, when x equals 3, we get 0 over 0. So finding holes is not something your calculator will do for you necessarily. You need to find them yourself. So when you are analyzing functions, whenever your zeros and your vertical asymptotes share a value, or if you have multiple values, you could have more than one that's being shared. Whichever ones they share, that is where you will have holes.